In example 8, we have this parallelogram. AB is equal to 12, BC equals 5, and the measure of angle C is equal to 62 degrees. So that's what we're given, and we're trying to find the area of this parallelogram. We have some formulas for parallelogram to find the area. That's base times height. The problem is 12 would be a base, 5 isn't the height because it's not perpendicular. So what we're going to do is draw in the perpendicular height. It is the height. I'll use the variable of x for that. I could have used a little h. I'm choosing to use x. So if I can find the value of x, that will give us the height of the parallelogram, and then that'll give us the area of the parallelogram. Now, focusing in on just that triangle that was created, we know that 62-degree angle in there, we know that 5 is the hypotenuse of that little triangle, and x is the side that we want in this right triangle. So using right triangle trig, we could say that sine is the trig function that relates all this together. Specifically then, we could say that the sine of 62 is equal to the opposite over the hypotenuse. Then when we multiply both sides by 5 with a little bit of algebra, 5 times the sine of 62 is equal to x. Now we're going to keep it like that for right now. At the very end of this, we'll go to the calculator and get the approximate area. But for now, I know that x, the height of this parallelogram, the distance between the top and the bottom, is equal exactly to 5 times the sine of 62. Now on to actually calculating the area. The area of this parallelogram is the base of 12 times the height, which we now know is 5 times the sine of 62. Just like for a rectangle, area is base times height. Same thing here in this rectangle, area is base times height. Base of 12 times the height of 5 times the sine of 62. We can multiply those to simplify it a little bit before we get to the calculator. And then here, we'll actually go to the calculator. Take 60 times the sine of 62, and that comes out to approximately 52.98 units squared. So we've done trig before. Now we're using trig not just to find lengths, but to find areas. So there's another application for us as to why trig is so useful for us. This actually leads to another formula. If we have a parallelogram, let's say I know that this length is A, this length is B, and we have this angle C. The formula to find the area of a parallelogram is kind of like what we had for the area to find a triangle. I'm going to draw in this one diagonal, and that's going to split the parallelogram into two congruent triangles. We know that in a parallelogram, opposite sides are congruent. So this is little b, this is little a. This is also angle C over here. And to find the area for this triangle, we had the formula before where we said that when you get no side angle side, you could do 1/2 little a, little b times the sine of angle C. So the area just of this turquoise triangle would be 1/2 little a, little b times the sine of angle C. The area of the bottom half of this one would also be 1/2 little a, little b times the sine of C. So the area of the entire parallelogram, more importantly to us then, is the sum of those things together. We want to add the area of this top one plus the area of the bottom one. So 1/2 this plus 1/2 that equals 1 whole. Specifically then, this is another formula for us. The area of a parallelogram is little a times little b times the sine of angle C. Another formula for us, this time to find the area of any parallelogram. I did all these calculations in the middle, but I can really erase all that stuff because we don't need to draw in anything extra here. All of this stuff is gone. As long as you know one side, the second side, and any angles, multiply the two sides times the sine of that angle, that will give you the area of a parallelogram. All right, example 9. L Guido is a regular hexagon. LG is equal to 10. And our goal in this problem is to find the area of that regular hexagon. We're not going to look at specific formulas for any shapes that have more than 4 sides. So pentagon, hexagon, heptagon, whatever bigger than that, we're going to do it kind of in the same process. Every regular polygon has an exact center, so we're going to put a point where that center is approximately where we think it's at. And then from that point, we're going to draw in radii. I call them radii because it comes from the center of the circle and it goes to the vertex. All of those are going to be the same. If we put a circle around this and hit each one of those vertices, that would be a circle, and this segment would be the radius. So we're going to draw in both of those radii, and they're both congruent to each other. That's because it's a regular polygon. And we want to figure out, in this triangle, what do we know? It is a regular hexagon, so what we can do is figure out how big is each angle in the regular hexagon, and then once we figure that out, we can divide it by 2 to figure out the measure of this little angle over here. We have a formula for that to find the angle of each angle in a regular polygon. That was n minus 2 times 180 over n. Go ahead and use that formula to figure out how big is each angle in this regular hexagon. So when you use this formula, plug 6 in for n, you get 120. And what that number represents is that each angle in this regular hexagon is 120 degrees. Because it's regular, there's a lot of symmetry, so that when we drew in this radius, it bisected that 120 degree angle, and now this angle is 60 degrees. This angle over here is 60 degrees. This angle over here is 60 degrees. We have a lot of 60 degree angles in there whenever we draw in one of those radii. We're not done drawing yet. We're going to draw in one more segment. We already drew in 2 radii. Now we're going to draw on this green segment. Now this green segment serves 2 purposes, really. It is the height of this triangle. So that's why it's significant, and that's why we're drawing it. So we have this yellow triangle over here, and that green segment is the height of it. For the entire hexagon, it's called the apothem. Sometimes it's called the apothem. It's pronounced either way. It's the apothem of the regular hexagon. More importantly, it's the height of this yellow triangle, and we're going to try to find that height to help us with that triangle. So focusing more now on just even this yellow triangle. We know a couple things about it. We know that this is a 60 degree angle, that's a 90 degree angle. So it's actually a 30, 60, 90 triangle, which makes it a special right triangle. However, we're going to use trig on it to find the length of this segment, which we'll just call x. The one other piece of information I know about this triangle is that when I draw in this apothem, it bisects each of these sides. So this small length here across the bottom is going to be 5. We've already studied right triangle trig, so then if I look at this yellow triangle and relate the important pieces together, from the 60 degree angle, x is the opposite, 5 is the adjacent, which means if I want to find the value of x, the trig function that brings that all together is tangent. So I could say that the tangent of 60 is equal to opposite over adjacent. With a little bit of algebra, we can multiply both sides by 5. I can use colors as I'm going through this. It might be a good idea for you to box off different things just so they don't all run together. So x, that length, is equal to 5 times the tangent of 60. Now here's why that's significant. I'm just going to call the center of the circle point C. I could call it anything I want to. But that yellow triangle is significant for us. We're going to find the area of it. The area of triangle LCG. We're going to go back to the most basic kind of area formula we have. The area of a triangle is 1/2 base times height. So in this yellow one, we're going to say it's 1/2 times our base of 10, 10's the entire base, going from L to G, times the height, which was x. We just calculated that to be 5 times the tangent of 60. And putting all this together, we have the area of that yellow triangle. Now, simplifying this just a little bit, can multiply these numbers. 1/2 times 10 is 5. 5 times 5 is 25. So here is an exact area for triangle LCG. Haven't really had to touch the calculator yet, which is kind of nice. Don't have any rounded numbers that need to be stored. That's the exact area for that triangle. Kind of block that off and go back to the point of this problem. We wanted to find the area of this entire regular hexagon. So far, we have the area of this one yellow triangle. Recognize again, this is a regular triangle, or regular hexagon. So if I were to draw in this segment, and this segment, and this segment, and this segment as well, now we see that there's not just this one triangle as part of it. There are 6 triangles that are inside of this regular hexagon, and they're all congruent to each other. So to find the area of this entire hexagon, we just multiply the area of that one triangle by 6. So it's 6 times 25 tan 60. That'll give us the area of the entire hexagon, not just that one triangle. Once again, before I go to the calculator, I can multiply 6 times 25 and get 150. And then definitely at this point, we'll go to the calculator to get an approximate answer. Take 150 times the tangent of 60, and that's 259.81 units squared. Example 10, NAT is a regular triangle. NT equals 15, so all the sides equal 15. This is the case where we know all 3 sides of the triangle, so we could use Hero's formula. First, we have to find the S value, or the semi-perimeter. Add up all 3 sides together, divide by 2, and S comes out equal to 22.5. Exactly 22.5, so we can use that decimal. Now the area is big square root of S times S minus A times S minus B times S minus C. So those are the numbers that we're going to multiply together, and then take the square root of all that, and that'll give us a final area of about 97.43 units squared. Number 11 is a regular octagon, and we don't have to draw the entire regular octagon in order to solve this one. What's important, though, is that we can draw 3 consecutive sides, and then I'll put a point where I think the center would be. The perimeter is 40, and since there are 8 equal sides that all add up to 40, that means that each side of the regular octagon is equal to 5. Like the other problems we've done, we're going to draw in a couple of radii. Also, we'll draw in this apothem, which bisects that 5, which makes this little length 2.5. Focusing on this right triangle, I want to know this length of x, which is the height of this little triangle, the apothem of the entire octagon. I need to know this angle down here in the corner. We're going to take 8 minus 2 times 180 divided by 8, our formula to find each angle in a regular polygon. Each angle is 135, so then if I divide that by 2, that makes this angle exactly 67.5 degrees. Now working with that yellow triangle, that yellow right triangle, we're going to use trig and say then that the tangent of 67.5 is equal to opposite over adjacent. Multiply both sides by 2.5. So then the value of x, the height of that one little triangle, or the apothem of the entire octagon, is equal to this. Block that off. The area of the triangle then, of this turquoise triangle, is going to be 1/2 times the entire base, which was 5, times the height of that triangle, which we just found to be 2.5 times the tangent of 67.5. If we multiply the coefficients out front, we would get 6.25 times the tangent of 67.5. So here is the exact area for that turquoise triangle. We don't stop there because that's just the area of that triangle. We have to go a little bit further. So I'll block that off. We want the area of the entire octagon. There are 8 turquoise triangles inside of this octagon that are all congruent, so we'll multiply 8 times that area. If you take 8 times 6.25, you get 50. So the exact area of the octagon would be this, 50 times the tangent of 67.5. And at this point, I'll go to the calculator to get an approximate answer. And that's going to be about 120.71.